This episode is brought to you by Brilliant. This diagram represents the first mass-produced electrical system in human history. It was incorporated into the most common variants of the Model T, and it consists of basic wiring that integrated a magneto-powered ignition system, lighting and a horn, and a generator and battery combination that was used to primarily drive the starter motor. Over its 19-year production span, with 15 million units produced, the Ford Model T's electrical system had evolved drastically. Initially launched with a starterless, minimalist configuration, it would gradually incorporate components that can be found in the electrical systems of modern vehicles. Even from its early beginnings, automotive electrical systems exhibited a clear trajectory towards growing sophistication and complexity. Early automobiles, including the Ford Model T, used cloth-covered wire. This type of wire consists of a copper conductor insulated with a layer of cloth material. The cloth insulation was typically made from cotton or a similar fibrous material and impregnated with a varnish or rubber to provide additional protection against moisture and wear. While solid copper conductor wiring was commonly used in the vast majority of applications at the time, automotive wiring was made of stranded wire, consisting of multiple small wires. Stranded wire was developed in the late 1800s to address the limitations of solid wire, particularly in applications requiring flexibility and durability, especially when exposed to vibration. Cloth-covered wiring impregnated with rubber specifically proved to be ideal for automotive use, as its flexibility made it easier to route through confined and complex spaces. These wiring assemblies were typically connected to components via a termination that consisted of a solder-on ring terminal that was fixed by screws, with longer spans of wiring being secured with metal clips and even staples. This technique was used even on high-voltage ignition wires. Fully rubber-covered wire was also developed as a more durable insulation option, and while it was superior in flexibility and insulative properties over cloth-based variations, rubber insulation became brittle and cracked over time, especially when exposed to heat, light, and certain chemicals. Early automobiles were notoriously unreliable, and their electrical systems greatly contributed to this. Over time, cloth insulation deteriorated, especially if exposed to moisture and oils, leading to a risk of shorts and electrical failures. Cloth insulation also offered less protection against abrasion and chemical exposure when compared to modern insulation. The wiring terminals used were bulky and suffered from failure due to fatigue caused by vibration and heat cycling. This also caused threaded fasteners to back out, breaking electrical connections. These junction points were also susceptible to contamination and corrosion, further diminishing reliability. In the 1930s, bullet terminals were one of the first fastener-less connector systems to appear on vehicles. Bullet terminals consist of a male component, the bullet, and a corresponding female component, the socket or sleeve, into which the bullet fits snugly. These connectors are usually made from soft metals such as brass or tin-plated brass, which are chosen for their good electrical conductivity and resistance to corrosion. The exterior of the connector often features an insulation sleeve made of vinyl or rubber to protect the connection. A variant of the concept called spade terminals would also be developed that permitted a connection to be used in tighter spaces and harsher physical environments. Spade terminals consist of a flat, spade-shaped male connector that places the mechanical connection to the outer ends of the terminal via a barrel-shaped spring-like clamp on the female end, while the center of the terminal forms the primary electrical connection. Many versions also incorporate a third center locking mechanism along the terminal's body for a more positive connection, particularly in high vibration environments. The low-profile nature of spade terminals allow them to be made into tighter reach variations such as 90-degree flag-style spade terminals. The 1930s also saw the introduction of crimping to terminate wire terminals. Crimping involves mechanically compressing a terminal around a wire to ensure a metal-to-metal contact. It offers a quicker and more reliable method for making connections, especially in production environments where speed and repeatability are essential. It avoids the application of heat and when done correctly, provides excellent mechanical strength and a high degree of resistance to vibration and pulling forces. Crimping also ensures a consistent and uniform connection, reducing the risk of cold joints or other soldering defects that can lead to failures. It also retains the full flexibility of the wire near the connection point, unlike soldering, which can create rigid sections that may be prone to fatigue and cracking under stress. Crimp terminated connections not only made vehicle wiring far more serviceable and cheaper to manufacture, but also dramatically increased reliability through the inherent strain relief they provided. By capturing a wire's insulation within a crimp, the stresses and strains placed on the cable are prevented from being transferred to the conductor, dramatically reducing fraying, breaking, or pulling out from the terminal. Additionally, strain relief is also provided by any sleeves used on the terminal junction. Towards the end of the decade, aircraft electrical systems were growing so complex that single junction connections were becoming impractical, especially for military use. Electrical aviation components sometimes required a dozen or more connections, all of which had to be easily disconnected for service while remaining securely connected in harsh environments. This was especially critical in combat situations. In the US, aircraft manufacturers would ultimately adopt a solution that was traced back to the early days of the motion picture industry. Back in the 1920s, studio lighting required a connector that could not be accidentally disengaged. This need was met in 1925 with the introduction of a receptacle and a plug with a mechanical locking ring. Called the M series, it was developed by Robert Cannon, the founder of Cannon Electric. By the late 1920s, Paramount Studios developed its own P series connector for a new sound camera that utilized a latched locking device, while Fox Studios would introduce its own threaded coupling ring variant. From these concepts, the threaded ring circular connector design was found to be best suited for aviation and would be first used on the Douglas DC-1 aircraft. Circular or cylindrical connectors consist of two mating halves or shells, each of which contains multiple pins or socket configurations. Internal insulating spacers, initially made of hard rubber, support the contacts in their proper orientation. The plug end is attached to a wiring bundle while the receptacle is often mounted in a fixed position, such as on a panel or case. The plug consists of a barrel, a coupling nut, and a back end termination. The barrel fits inside the receptacle shell, and the coupling nut holds the mated pair together. Alignment of pins and sockets must conform to rigid tolerances during the manufacturing process in order to avoid bending or breaking during separation or closure of the two halves. Wires are attached to the individual contact pins by crimping or soldering and are held in place by either an interference lock, a contact lock, or an insert lock. The locking mechanism determines how the pins are inserted. The shells were usually fabricated from aluminum or steel and were extremely rugged and were also polarized to prevent mismatching and to make assembly easier. The success of these connectors led to the United States Department of Defense establishing military specifications to create a supply of standardized components with defined housing dimensions and pin layouts, specifically designed and tested to withstand the reliability, performance, and environmental requirements of the application for which they were intended. The first of these military specifications was the AN 9534, which appeared on November 1, 1934. The specification was superseded 2 years later by AN WC 591, which was used with various revisions for the duration of World War II. The growing importance of air power during the war led to the establishment of the U.S. Air Force as a separate branch of the military, with a whole new set of connector requirements. In 1949, MIL C 5015 superseded ANWC 591 and became the first coordinated connector specification approved for use by all three services, Army, Navy, and Air Force. Considered the progenitor of all connector specifications, MIL C 5015 covered a broad range of pin contact sizes and voltages up to 3,000 volts AC. The development and introduction of synthetic polymers in the 1920s and 1930s marked a turning point for the electrical industry as a whole. Plastics were found to offer superior characteristics over impregnated cloth and even full rubber wire insulation. It was far more resistant to abrasion, electrical and thermal degradation, and unlike previous installations, could be chemically adapted to a broader range of applications by altering its physical properties. One of the first and most popular plastics to be used for wire insulation was polyvinyl chloride. During World War II, PVC was introduced as a replacement insulation for rubber, as the US lost access to 90% of the world's natural rubber supply. Its thermoplastic properties made it very easy to manufacture as it became more plastic when heated and rigid again on cooling. It also allowed for the mixing in of stabilizers, plasticizers, flame retardants, and lubricants to achieve a broad range of properties. PVC insulation was designed to be resistant to a wide range of temperatures, from -40 degrees Celsius to 125 degrees Celsius, as well as to abrasion, moisture, and atmospheric agents including UV rays. It can also safely insulate up to 1000 volts. PVC insulation, however, when exposed to hydrocarbons and chlorinated solvents, can degrade or become brittle, leading to insulation failures. It can also become rigid and less flexible at lower temperatures, and when exposed to fire, PVC insulation produces thick black smoke, hydrochloric acid gas, and it emits dioxins, which are highly toxic and can cause health issues and environmental damage. During the 1950s, vehicles began incorporating radios, climate control systems, power windows, wipers, more lighting, and various other amenities, transforming vehicle wiring into its own complex subassembly known as a chassis wiring harness. Much like with aviation, multi-pin connectors were needed, but the bulky and costly connectors used in aviation were not viable for a consumer product. The solution came in the form of the industry adopting its own range of less costly, plastic-based multi-pin connectors. Made from nylon, these early connectors were injection molded into a pair of rectangular mating shells that housed spade terminals that were set in place by a contact lock on the terminal body. The shells were locked together by a combination of friction and a simple clasp that was captured in an integrated aperture. Rubber boots were often used to protect the connection in exposed areas on a vehicle. While these connectors were far less durable and were limited in terminal count, when compared to their aviation counterparts, they were sufficient enough for automotive use at the time. Over the next 2 decades, solid-state electronics started to appear in vehicle electrical systems, initially within specialized function components such as voltage regulators, electronic fuel injection drivers, wipers, and lamp and wiper controls. Wiring harnesses were growing denser and far more signaling and sensing functionality became a part of this new era of vehicles. Chassis wiring harnesses were now designed using a broad range of wire cross-section areas, insulation materials, sheathing, and connector types to specifically accommodate a section's application while balancing cost and reliability. The mid-20th century also saw the introduction of new wire insulation materials based on propylene, polyethylene, tetrafluoroethylene hexafluoropropylene, ethylene tetrafluoroethylene, polyurethanes, polyesters, polyamides, and synthetic rubbers that all offered varying degrees of better electrical characteristics, greater resistance to temperature, abrasion, and hydrocarbons when compared to PVC, with some even allowing for thinner insulation walls, though these more advanced insulations were used only when needed due to costs. Ethylene tetrafluoroethylene wire in particular was adopted by motorsports alongside mil-spec circular connectors due to its electrical properties, chemical inertness, and exceptional impact strength. Known as Tefzel wire, its thin but tough insulation allowed for less bulkier but extremely durable wiring harnesses that could withstand the extreme environments of racing. In the 1970s, stricter fuel efficiency regulations in the United States forced car manufacturers to improve engine efficiency and reduce emissions. When combined with the exploration into the performance benefits of fuel injection by European manufacturers, the progressive adoption of electronic engine management systems would occur over the next decade. These changes had a dramatic impact on wiring complexity, with electrical systems now incorporating dozens of sensors and control mechatronics. From this, multi-pin connectors were now capable of containing up to 100 connections, with the pin and socket design becoming standard. Similar to aviation connectors, these use contacts made of precision stamped and folded thin sheets of brass or copper alloys that are formed into cylindrical pins along with a respective matching socket. Their mating shells are generally rectangular, though more complex shapes are common, with equally various forms of integrated keying for orientation. Pin and socket connectors tend to use a combination of contact locking and varying forms of insert locking, such as wedge locks. This was particularly important not just for positive locking and ease of harness assembly, but also to distribute tension forces evenly across the connector body. Commonly made from either polyamides, polybutylene theraphthalates, ABS, or nylon, the precision injected molded shells employ one or more locking mechanisms to secure the halves together, ranging from clasps to external locking clips and even robust assembly force limiting locking mechanisms for larger connectors. Much like their mil-spec counterparts, silicone or Viton seals and wire gaskets are also utilized to weatherproof both the mating and wire termination end of the connector. With the proliferation of digital engine management in the 1980s, chassis wiring harnesses now had to contend with a new function: the transmission of digital signals and highly susceptible analog sensor signals. This becomes problematic with relatively inexpensive PVC insulations because of its higher dielectric constant. Dielectric constant indicates how readily a material polarizes in an electric field. Materials with a high dielectric constant store more energy, but this can cause signal attenuation and distortion at high frequencies. Additionally, signal lines have to operate in the electrically noisy environments created by the ignition and charging system and must be able to handle crosstalk from other lines within dense wiring bundles. To address this, wire insulation materials such as polyethylene and cross-linked polyethylene are favored for their low dielectric constants, offering minimal signal loss at high frequencies. For highly sensitive signals, such as in ABS sensors or NOx sensors, signal lines are sheathed often with grounded aluminum foil shielding to mitigate the effects of electromagnetic interference. Throughout the 1990s, computerization became integrated with automotive electrical systems, with network topology slowly being adopted by most manufacturers. In this model, electronic controllers were assigned to each vehicle system, and between them, multiplexing signal protocols allowed for multiple channels of data to be exchanged over a single physical channel. The first multiplex systems used basic serial protocols derived from industrial systems, such as RS-232, RS-485, and RS-422. These protocols rely on a predefined fixed bit rate and some connection management data to directly transmit a stream of bits. The simplest form of this is known as single-ended communication, where a bit is represented by a voltage level relative to ground. While this only requires a single signal wire and is simple to implement, its bitrate is limited due to noise susceptibility. Balanced serial communication improves this by using two signal wires that are often twisted together. One carries a positive signal and the other carries an inverted signal. Any noise induced on the transmission line affects both signals equally, allowing the receiver to effectively cancel out the noise by subtracting the inverted signal from the positive one. This method improves noise immunity and enables reliable faster communication over longer distances when compared to single-ended serial communication. In the early 1980s, various automotive serial communication protocols emerged, such as K-line, L-line, J1850, which used pulse width modulation, and SCI, used by General Motors. These protocols facilitated diagnostics and intermodule communication, but lacked speed and flexibility. In 1986, Controller Area Network Bus Protocol, or CAN bus, was released at the Society of Automotive Engineers conference in Detroit, Michigan. Developed by Bosch, CAN bus is known as a multi-master serial bus, as it permits multiple nodes to communicate with each other over the same channel, robustly and without conflict. CAN bus employs two wires that carry opposite bit states, or a differential signal, to easily filter out noise. The specification also defines a messaging protocol that encapsulates intermodule communication into frames with advanced features such as prioritized message transmission and error detection. By the mid 1990s, it would be adopted by the industry as the standard for in vehicle digital communications, with the standard evolving over time to support higher data rates and larger payloads. By the mid 2000s, dozens of subsystems were now common on vehicles, with vastly different requirements. Critical systems such as ABS, airbags, traction control, and engine management require low latency, robust links, while basic chassis electrical systems can operate efficiently on low speed, simpler communications. Infotainment systems, in comparison, require high data rates, but are not critical. Because of this variability, modern vehicles now operate multiple networks, with some even using fiber optics to facilitate high data rates and noise immunity. A typical mid 2000s vehicle configuration, for example, would employ a CAN bus network for critical systems, a single ended low speed serial bus such as LIN for non critical chassis electrical control and human interface, and a fiber optic protocol such as MOST for transmitting digital audio data throughout an audio system. Vehicle service and diagnostics has also benefited by the use of multiplexing networks by allowing the direct access to the control systems within a vehicle from a singular interface. Though this comes at the cost of expensive diagnostic tooling, training, and reliance on manufacturers for proprietary hardware. As advanced driver assistance systems, or ADAS, began to appear in vehicles, high bandwidth links that are capable of handling video data added a new layer of vehicle networking. Two common technologies used for this are standard Ethernet adapted to vehicle use and FlexRay high-speed deterministic bus network, a CAN bus-like system that is designed for time-critical applications in vehicles. With the introduction of hybrid and electric vehicles, an entirely new realm of evolving standards have emerged that encompass various aspects of EV wiring, including the design, installation, and performance requirements of high-voltage wiring harnesses, cables, connectors, and associated components. Standards such as ISO 15118, IEC 62196, and IEC 61851 define communication protocols, connectors, and charging infrastructure specifications to facilitate seamless interaction between EVs and charging stations. Additionally, standards like IEC 63110 and ISO 6469 establish safety requirements for high-voltage cables and electrical systems in EVs to mitigate risks associated with electrical hazards. The automotive industry is experiencing a profound transformation, navigating the shift from traditional combustion engines to electric power while balancing performance and the allure of driver experience with the potential rise of autonomy. However, despite this potential paradigm shift, one constant remains: the critical role of wiring in vehicles. It's the little progressive changes over time that pushes an industry forward. The automotive electrical industry is a perfect example of this. Small changes in materials and designs over the decades laid the foundation for the incredibly sophisticated digital vehicle systems of today. And at the heart of any advancement is the process of testing and measurement. Building a strong grasp of measurement and analysis can be complicated, but there's a free and easy way to get started immediately. That's where Brilliant.org comes in. Brilliant.org is my go-to tool for diving headfirst into learning a new concept. It's a website and app built off the principle of active problem solving. Because to truly learn something, it takes more than just watching it. You have to experience it. Brilliant is constantly developing their courses to offer the most visual, hands-on approach possible to make mastering the key concepts behind today's technology effective and engaging. A great starting point I highly recommend is Brilliant's measurement course. In this series of lessons, you'll unlock your sense of perception and learn how to quantify information in new, more meaningful ways using an intuitive set of exercises that'll change your perspective. With Brilliant, you learn in depth and at your own pace. It's not about memorizing or regurgitating facts. You simply pick a course you're interested in and get started. If you feel stuck or made a mistake, an explanation is always available to help you through the learning process. To try everything Brilliant has to offer free for a full 30 days and start learning STEM today, visit brilliant.org/newmind or click on the link in the description below. The first 200 of you will get 20% off Brilliant's annual premium subscription.